Well, hello and good morning or good afternoon or good night, whatever time you're watching this. I don't know. Hey, team! Dr. Locke's chemistry coach coming at you. We're going to be talking about spectrophotometry, at least the spectrophotometry lab. So, this is kind of the pre lab material for that. And what's kind of neat about this lab, it's very distinct than all the other ones that we're doing because it doesn't follow information from the textbook that we're doing. You're not going to see this kind of stuff necessarily on your quizzes or exams, but it's such a common technique, possibly one of the most common techniques as you move up in science, whether it's biology, chemistry, whatever. Maybe you'll transfer to a university, maybe do some master's level, PhD level work. When I was doing that kind of stuff, the majority of my labs and research involved taking some form of electromagnetic radiation, EMR, aka light, right? All the different regions. So you might want to review some of your first semester of general chemistry stuff on electromagnetic radiation, the electromagnetic spectrum, infrared, ultraviolet, visible, nuclear, X-rays, all those different regions of the electromagnetic spectrum, the relationship between the speed of light, wavelength, frequency. That would be a good review for that. Any of those kinds of labs. But what we're essentially doing is just taking some form of the electromagnetic spectrum, whatever region it is, infrared, ultraviolet, yada, yada, and strike some matter with it, right? Whether that matter is a gas or it's maybe some ions in a solution, a solid, whatever it is. Typically, we're going to use solutions at this level and analyze matter that way. So that's fundamentally what spectrophotometry is, but there's lots of specific ones. There's like infrared spectrophotometry, right? So if you use the infrared region, which you'll probably do in organic chemistry, remember infrared radiation, when you strike that upon certain types of matter, it can cause the vibrational excitation of bonds. So like a carbon-oxygen double bond versus a carbon-hydrogen single bond, they're going to vibrate at different frequencies. Of course, that would absorb different types of energy. So we're going to have to talk and a brief review of absorption of energy, a real brief one, but you could review the Bohr diagrams and things like that from quantum mechanics if you want to. So we're not going to do that at this level, but organic, you'll probably do some infrared work. We're mostly going to focus on visible UV, like called UV VIS Spectrophotometry, where we take either ultraviolet or visible light. We're going to be using visible light, striking matter with that. And as you probably remember from first semester of general chemistry, that can cause electron excitation. We're going to take a brief look at that on the next board. But two fundamental things we could do. We could do qualitative work where, hey, we don't really care about quantities. We just want to know what is it, right? And I remember doing that in organic using infrared light, look at the different kinds of bond energies, and from that I could look on some standard table or do a computer sometimes today can just do the search for you. Tell this is the molecule, and it'll tell you what it is, what types of bonds in there, and sometimes it's like a game. You can put the pieces together. Oh, this has a carbon-oxygen double bond, sulfur-hydrogen single bond, whatever it is. You can put this molecule back together and figure out its identity. So that's qualitative. We're not going to be doing that for this particular lab for Chem 185. We're going to do quantitative work. So we're going to take light, specifically visible light, strike a solution with it, and look how many photons of that light are actually absorbed, right? Oh, this looks quantitative to me. Concentration, that's the amount of a solute in a particular solution. So we're going to look at things called Beer's law later in a couple boards and be able to relate the concentration of some particular species to how much light or how many photons it absorbs. Quantitative analysis, pretty cool. Let's do a real brief view of electron excitation, right? And the relations between wavelength and energy and all that fun stuff. But I highly recommend watching some old videos or reviewing your notes on it. Be right back. Do you all remember your Bohr diagrams from first semester of general chemistry, quantum mechanics? This was kind of the meat and potatoes of that. And just going to take 1 minute to review it real quick. So remember, you've got these quantized electron energy levels, whether this is, a neutral molecule, an ion, whatever it is in solution. And they all have their own unique energy levels, right? So, n equals 1, n equals 2, 3, 4, 5, they get closer and closer together all the way up to n equals infinity, where you've removed the electron from the species. But if we've got, say, a situation here where we'll look at absorption of a photon, right? So we've got light impinging upon this sample of matter. So you've got a photon coming in, right? So a photon comes in. I don't know what a photon looks like. right? But let's say that's the photon here. Right, so you've got this particle of light coming in, blam! It hits that electron, and if that photon has a photon energy exactly equal to the energy difference between two electron energy levels, boom! It can get excited. It climbs up the ladder. For example, it can get excited up to, say, n equals 4. Right? We call that excitation. And there's various songs I could sing about that, right? Which I'm not going to. Boom! It goes up to an excited state. Okay, now typically samples don't like to do that, so you'll get a situation where maybe you've got an electron in an excited state and it relaxes back down. We call that relaxation. And we can study spectrophotometry either way. We could do absorption spectrophotometry, or if we do relaxation, they call it, right, emission, right? We can look at the emission of photons. So we can hit a sample with light, measure and let the electrons get excited, or even not electrons, it could be anything, right? But we're going to focus on electrons for this particular lab, and then let those relax and measure the light coming out after relaxation, right? So when it relaxes like this, boom, it releases a photon, and that photon will have an energy exactly equal to the energy difference between those two levels. So you can get lots of different, you can go 4 to 3, 4 to 1, 1 to 2, just depending on the, for absorption, depends on the energy of the photon. And that's why particular solutions have particular colors, right? So I can take white light of all different wavelengths of the visible region, strike a sample, and maybe just a few of those wavelengths, right? Maybe in the bluish region, or maybe in the yellow region, or the reddish region get absorbed. Everything else goes through, and we see what gets through. We see the complementary color. So it's kind of cool. So you can kind of almost estimate what wavelengths a particular species will absorb based on the color that you can observe of a solution. You can look on the stock shelves. You can see greens and blues and reds and yellows. It's kind of neat, right? Oranges. And in this situation, boom, it would emit particular photons, and we could see colors coming out if it was in the visible region. Nice, huh? If it's outside visible, we'd need, our pathetic human eyeballs would need better detective techniques to notice it's ultraviolet or infrared or something coming out. But remember, that energy difference between two electron energy levels must equal the energy of the photon. And if you remember Planck's equation, that equals the Planck's constant times the frequency, or if you substitute in Planck's constant times the speed of light divided by the wavelength. And I box what we're going to be using, relating wavelength to energy. So the smaller the wavelength, the higher the energy, etc., etc. So just wanted to review that real quick. Let's take a look specifically at what are called absorption spectrums, what we're going to be focusing on, and how we can quantitatively relate the absorption of photons of light to the concentration, which is what we're ultimately after, to be able to take a solution, and I give you that solution, you can blast it with some visible light and come back and say, this is the concentration of your unknown. Where's my maximum points? Thank you, coach. All right, bit of a busy board here, but let's take a look at it. So imagine we take some sample. In our case, we're going to put a solution in a little holder called a sample cell, specifically a cuvette, by the way. Really fun to put that in the spectrophotometer. It's going to be fun when you can actually see the spectrophotometer in lab, open it up, and we'll show you all the different parts and components and let you run it. It's kind of cool. So let's put some solution, and if we're going to use visible light, it's got to have a color to it. That's why we use water as a solvent, because water's colorless, so it doesn't absorb in the visible region. Yay! It'd be kind of silly to use a solvent that absorbed in the same region as the solute you're trying to analyze. Right? That wouldn't be smart. You have to worry about the sample cell holder as well. You want to make sure that that's some kind of material that doesn't absorb in the same region of interest also. And you have to watch out for scratches and fingerprints. You don't want to get a fingerprint on there because that could scatter some of the light, meaning that light doesn't get through, and we're going to perceive that as being absorbed, so we're going to get high concentrations. Right? So there's lots of little kinds of errors that can happen if you're sloppy in spectrophotometry. It's easy to do. Put sample in cell. Put cell in spectrophotometer. Hit button. Readout. Yay! It's not hard, right? It's like driving a car. Right? You get in. Once you learn how to do it, it's pretty easy. But changing your tire, changing your oil, fixing your transmission, fixing a fuel injector system. I mean, that's a whole different ballgame, right? So that when things go wrong with our spectrophotometer, we got to hire in the professionals, pay them a lot of money, and say, please fix it. It's broken. I don't know why. But let's say we take some initial, right, this little sub-knot, that's our initial light intensity coming in, which is a certain number of photons coming through, right? You know, per second, say photons per second. Boom, some get absorbed, not all, some get absorbed, so there's less light coming out, so it's a lower intensity. We'll call that the final intensity, right? We can measure the decrease in that intensity. So quantitatively, what does that look like? Well, it depends on how long it travels through that cell, right? So we have to measure the length of that cell. We call that the path length with B, right? If it's a longer cell, more photons will be absorbed. If it's a shorter cell, less photons would be absorbed, right? Makes sense? Can you see an equation coming that involves B, the path length, and how much is absorbed? And the more particles of solute in there, the more, if there's more particles of solute, you're more likely to intercept a photon, correct? So would it make sense that the concentration, the higher the concentration, the more photons get absorbed? The higher the path length, the more photons get absorbed. Oh, you could probably create an equation on your own right now. We're getting there. Next board, we'll get the equation. Like, I just want to see the equation. Where's the equation? I want you to understand why the equation is what it is. So here's the basics of this entire thing. Now, there's a lot more components we're going to show later for the spectrophotometer to make this work, but this is the central piece. Sample, hit it with some incident light, some photons get absorbed, less light gets through, measure that. So we can measure the initial intensity and the final intensity, well, a computer can. And there's two ways we can look at this. We can look at how much light gets through. That's called transmittance, capital T. And that's just the ratio of the initial intensity, the final intensity to the initial intensity, right? So if it's the same on both sides, if no light gets absorbed, this would be a transmittance of 1, right? Pretty straightforward. Or you can multiply that by 100, and so that'd be like 100% transmittance. In infrared spectrophotometry, you'll probably use transmittance in organic chemistry. Well, here we're going to do VIS absorption spectrophotometry. So absorbance, A, is how much does not get through, right? Transmittance, how much gets through? Absorption, how much does not get through? And they're obviously related, but logarithmically. So absorbance is actually negative of the base 10 log times of the transmittance itself. So absorption actually has, and transmittance don't have units. You can see the units would cancel out here. And since you got the log term, etc., absorbance has no units. You'll see on the spectrophotometer, it'll say like, 0.721 ABS, just absorption. But that's really not a unit. It is a unitless quantity. So I put a little star here. We're going to be doing absorption spectrophotometry. Let's start looking at this equation we're going to get to. Be right back. All right, so when you remember the Bohr's diagrams, there was lots of different electron energy levels. So when we're absorbing light, there could be more than one wavelength. You can go from n equals 1 to 2, 1 to 3, 1 to 4, 2 to 3, 2 to 5. All right, there's a lot of different wavelengths. And when you're in a solution, that can you don't get these really nice lines. Usually you need, a nice solitary particles in the gas phase to get these nice lines. So when you put it in a solvent, the lines start to spread out and blend out, and you get what's called an absorption spectrum. If you plot the absorbance, right, that we measure versus wavelength, for example, so let's take a sample, and you're going to do this in what's called spectrum mode. It's going to be one of the first things you do, and we'll talk about why in a second. But you're going to take one of your samples, stick it in the spectrophotometer, click on spectrum mode, and say, go! And what it's going to do, it's going to run every wavelength through the visible region from, 400, I think it's like 390 or something, like 400 to 750 nanometers, give or take. Maybe 400 to 800, whatever it is, somewhere in that region. And it's going to send each wavelength in and see if it absorbs. So you'd be like, nothing, oh, a little bit, a little more, oh. And you're going to get us an absorption spectrum. Maybe it peaks out here, but it does have distinct areas where it absorbs more and places where it absorbs less or not at all. Our goal is to scan the entire visible region in spectrum mode and find the wavelength of maximum absorbance. Do you see that top right there? We call it wavelength max, and we got little tables that tells you what it is. Back in the old spectrophotometers, you'd had to physically move a bar around and find the one that's the top. You're like, this takes forever. Now you just hit a button and boop, it just spits it out for you and just read it off the computer. It's really easy to do. So our goal in the first part of lab is to figure out, run an absorption spectrum, take a sample, run every wavelength through the visible region, and go, what wavelength has the highest absorption? Boom! That's the first part. Not too bad. And then what we're going to do is take that wavelength of maximum absorbance and use that in what's called photometric mode to run all of our samples, right? So we'll have a bunch of different samples of known concentration we're going to do. We're going to have one with an unknown concentration, and we're going to measure the absorbance of each one of those at that specific wavelength to be able to do quantitative work in a little bit. All right, let me show you how to do that quantitative work with what's called Beer's Law, but that's going to be the first part of your lab, absorption spectrums. They're kind of cool. Let's put it all together. All right, we've already kind of taken a look at if you got that sample and you're shining light through it. Well, the longer the sample holder is, the longer the light passes through your sample, the more likely photons are going to be absorbed, right? So would it make sense that the absorbance is proportional to the path length? We'll call that B, right? A is B. This is called Beer's Law. It's really Beer, Lambert, and there's some other name there too. But most people just call it Beer's Law. Beer's Law, right? It's our favorite equation. So A equals epsilon BC. So we already know what A is. We already know what B is. That's your path length. So A is your absorbance, B is your path length. Typically the path lengths are manufactured, these cells, these cuvettes. I wish I had one with me, but I'm not on campus. I should have brought one back with me. But you'll see them. They're little cuvette holders. They're kind of cute. And they're typically manufactured to be 1.00 centimeters across, right? They could be, I remember in grad school, Jim Pitts Jr. was talking about doing some measurements where he took this laser and shot it across this field from one hill to another, bounced it off a mirror back to measure how much of that light was absorbed by particles and molecules in the atmosphere. And the path length was like 2 kilometers, like 1 kilometer there and 1 back. I'm like, whoa, that's crazy stuff, right? I love atmospheric chemistry was my thing. It was a lot of fun. But we'll just do our little 1 centimeter, 1.00 centimeter. Not exact, right? You can't manufacture things to an exact length. Well, what's this little epsilon thing? Well, we'll get to that last. Now, remember concentration we talked about. The more particles of solute there are that the light passes through, the more likely they're going to be intercepted, all right? Stupid analogy number 1. You have a swimming pool, right? You put an alligator in a swimming pool. You want to swim across without getting eaten. Well, if there's one alligator, right, there's a certain % chance you're going to get taken out. Well, if you put 20 alligators in there, well, you're more likely to get taken out, right? So the alligators would be your solute particles and you're the photon, right? More alligators, more likely they're going to take you out. Horrible analogy, but whatever. And then the longer the swimming pool, the more time the alligator has to get you. Right? The length of the swimming pool is the path length. All right, you'll probably never remember how stupid, you'll never forget how stupid that analogy is, but it works, right? So C will be the concentration, and typically we do molarity. It doesn't have to be, but that will determine the units of this proportionality constant called the epsilon, or the molar absorptivity. So if you're using molarity as your units of concentration and centimeters as your units for the path length, your molar absorptivity will have units of inverse molarity, inverse centimeters. Remember, absorption has no units. So this constant, this molar absorptivity, has to cancel out the units of the path length and the concentration. So it has to be inverse centimeter, or whatever length you're using, and inverse molarity, or whatever concentration you're using at the time. So what is this proportionality constant? Molar absorptivity is, think of it as the tendency for a particular species to absorb light at a particular wavelength. Right? So, and it's unique for each species. So, think of it as like, a specific heat or something like that. It's just based on the structure of the molecule. We're not going to get into details of that, but that's essentially what that is. So we can use this equation, and I'm going to show you how we're going to do this, how we're going to do a bunch of knowns. We're going to take 4 samples, 4 solutions of known concentration, measure their absorption, and we're going to use this equation to make a plot. All right? We're going to plot that, called a calibration curve. And once we get that calibration curve and do a least squares fit, we'll get a y equals mx plus b. Review the graphing video. We'll get a y equals mx plus b equation. See if you can get y equals mx plus b out of this. What is y? What is x? What is b? What is m? And once we have that equation, we can run an unknown, measure its absorbance, calculate its concentration, lickety-split. That's the goal, to get the y equals mx plus b. Let me show you how we're going to set up calibration curves, right? But this is the key to it all, Beer's Law. All right, hopefully this makes logical sense to you. We're going to do what's called a calibration curve, or a calibration plot. This is something we do a lot as you move up to higher levels of science. So we're going to make several known solutions, right? This requires hands-on technique skills. We're going to be in this lab pipetting. We're going to give you a base stock solution of a known concentration, and you're going to pipette out a certain amount of that. You're going to use a 2 milliliter pipette, which has an aliquot of 2.00 milliliters. You're going to pipette out, do all the conditioning and all that kind of stuff, pipette out 2 milliliters of a 2.00 milliliter aliquot of your solution into a 10 milliliter volumetric flask, diluted up to 10 mils. Shake it, shake it, shake it like a Polaroid picture, and boom! You can use your dilution equation, C1V1 equals C2V2, to calculate its concentration, right? You diluted it. Then we'll do another solution where we pipe out 2 aliquots. 2 times 2 milliliters is 4, or 4.00 milliliters. Dilute that to 10. That's your second solution, so it's more concentrated. Then we'll do another one with 3 pipette aliquots. 3 times 2 mils would be 6, or 6.00 milliliters. Dilute that to 10. And then the last one we'll do 4 aliquots. Pipette out a 2 milliliter aliquot 4 times, so that gives you 8.00 milliliters diluted to 10. So you'll have 4 solutions of increasing concentrations that you will be able to calculate. Then we'll run those, right? So we'll do the spectrum mode, figure out the maximum wavelength of absorbance. Then we'll do what's called the photometric mode. So this is part 2 of the lab. Run photometric mode, plug in that maximum wavelength of absorption, and then just run all of our samples in there, right? Measure their absorbances, plot them versus the molarity that we calculate. Boop. Of course, if you have nothing in there, it should technically go through the origin point here, 0. Boom, and we get a straight line. Well, ideally, unless you make boo-boos and the dots are way over the place, if you screw up your pipetting technique, doesn't go well. So you want to do good on your solution preparation. Ideally, we should be able to do a least squares fit. When you do a least squares fit, you get y equals mx plus b. Well, let's figure out what all these are. So we get y. See, this is our y-axis, right? So the absorbance is y. Concentration, right? We control the concentration. That's the independent variable. The absorption depends on the concentration. So that's the dependent variable, which goes on the y-axis. The one you control, the independent variable, goes on the x-axis. And one of these, there's an abscissa, I forget the mathematical names for those. All right, well, concentration is the x term, right? So absorption is y, absorbance is y, concentration and molarity is x, which means these two constants multiplied together, the molar absorptivity coefficient and the path length, are m, right? So the slope equals m equals the molar absorptivity times the path length. If we know the path length and the slope, you can calculate the molar absorptivity coefficient. You're going to be doing that in lab today. You can actually do it. That's how they do it, right? But where's the b? Well, if that goes through the origin point, that should technically be 0, right? So really it's this. See that? So that goes to 0. So we just don't include that in there. That would just be very, very silly to do. So this is where Beer's law, when you do a least squares fit, looks like y equals mx plus b. Bingo! So you're going to make a calibration curve, and then once you have the y equals mx plus b, you can run an unknown, right? Measure the absorbance of the unknown, correct? So we'll know the absorbance of the unknown. We'll know the slope from our least squares fit. We know our y-intercept, which should technically be 0. So we can calculate the concentration. As long as you know the absorbance, the slope, and this, you can calculate that for any unknown. You can eyeball it. So let's say our unknown is there. You can just eyeball it over and down and go, hey, there's my concentration, right? Very nice. Within this, if it's up here, you have to extrapolate it out and assume it's still linear, right? So we can do it by eyeballing it. What you're going to do is you're going to create your own calibration plot and eyeball your unknown, which is fairly accurate. And then we're going to calculate it using Beer's law this way. All right, so that's the essence of the lab, spectrum mode, photometric mode. But it really banks on your pipetting techniques here. I want to do one last board kind of looking at the components, because you're going to go to the spectrophotometer like a car. You can drive a car, but never open up the hood and know what the pieces do. And that's okay. You can run a spectrophotometer, stick the cell in there, hit the button, right? Anybody could really do that. Yeah, all my kids could do that and not have the faintest idea how a spectrophotometer works. But if you ever get the chance, if you're a chemistry major, to take analytical chemistry, you get to open up the box, open up the hood, look at all the pieces and see how they work. It's a lot of fun, actually. I really enjoyed analytical chemistry. So I want to look at the different components of it real briefly, just so you get a feel for what's going on under this plastic hood that you'll see when you go in to run the spectrophotometer. All right, this board is really busy. Normally I do this on a gigantic whiteboard in lab, so I get this little tiny one in my house. Let's squish this baby on here. And again, this is, if you're in my class, this is all in your Gen Chem notes. I believe it's like pages 140 to 145 in your general chemistry notebook, but hey, whatever. I'm just summarizing it for you. All right, 5 basic parts of a spectrophotometer. Of course, the main part is the sample that you put in there, but you can't do anything without a light source, right? So part 1 has to be your light source. And depending on whether you want infrared, ultraviolet, visible, X-rays, right, you're going to have a different type of source. A couple things about the source. You want it to be stable. You don't want the intensity fluctuating around all over the place. And you want it to be continuous, a stable, continuous light source. Ka-ching, you're going to pay some moolah for that. Typically, in the visible region, you're going to have a tungsten lamp giving off this polychromatic radiation, i.e. white light, right? If you want ultraviolet light, usually it's a hydrogen discharge tube, low pressure hydrogen gas in a discharge tube, giving off ultraviolet wavelengths. And we can actually switch from one light source to the other, but don't you do it. We're staying with just the visible, right? And you got to warm it up. I like to start this in the beginning lab, give it 10, 15 minutes to warm up so we can get that light source to a nice, stable, continuous intensity. All right, so that's number 1. And you could spend entire weeks on any of these things in analytical chemistry. It's kind of fun. You can focus on just light sources, whatever. Well, this polychromatic radiation, all different wavelengths, isn't going to do us any good. Remember, we're going to be wanting to run our wavelength of maximum absorbance, a single wavelength, single. Mono, poly is many wavelengths or colors, one wavelength or color. So we've got to get this polychromatic radiation down to one wavelength. Well, how do we disperse all those wavelengths or colors and just pick one? We use what's called a monochrometer, getting it to one color or one wavelength. Typically, you'll use a prism or a diffraction grating, and I talked about both of these in Chem 180 if you had me for Chem 180. We use the diffraction gratings, which, you just have this little grooved metal surface, the light, all the wavelengths hit it, and they reflect off at different angles. And we can make a series of mirrors and lenses, little slits and an exit slit, so only one wavelength gets out. You can actually hear the motors of some of the stuff running. It's kind of cool. So I'm not going to get into details of that, but we use a diffraction grating, isolate a single wavelength, and that gives us our monochromatic radiation of initial intensity. Then we do, and that's the second one. 3, we put our sample cell in there. Boom, you're going to see on our cuvettes, we have 2 sides that are clear, 2 sides that are frosted. So you don't want to touch the clear sides. The light has to go through the clear sides. You don't want to do the frosted sides because some of the light would reflect off, right? If there's chips or bubbles and all these things, that can cause error. No fingerprints, all that kind of stuff. So, because if anything scatters off of that cuvette and doesn't get through, that will be measured as absorbance, even though it wasn't. Oh, error, error, error. So you want to take care with this. And make sure you've got enough solution in there where it's, it doesn't have to be the top. It's usually about 2/3 through, so the light actually goes through. You don't want the light going through the air. That wouldn't work. So we put our sample in there. Typically, we use a plastic one for visible regions because the plastic isn't going to absorb in the visible region much. But if you get to ultraviolet, plastic can interfere with that. So we typically use these quartz ones, which are more expensive. Or maybe you've got a solution that reacts with it, like we do some iodine stuff later that can react with the plastic. So we had to use the quartz. Be careful not to break those. They're pricey. One thing you got to watch out for is we want the absorption of just the solute. We're going to be doing an iron sample. We're going to be looking at iron 2 ions, I think, complexed in solution. Well, you still have to worry about the solvent and the cuvette. Remember, so the absorbance we measure, right? It drops down to this final intensity. That's the absorption of the solute, the solvent, and the cuvette. There's 3 things causing that, right? Mostly the solute. So what we have to do is run this again with what's called a solvent blank, which is the cuvette with just the water or whatever solvent you're using. Run that. That'll have a really tiny absorbance. Subtract that from the absorbance of the initial sample, and that will leave you with just the solute. That's what we're after. So you're going to see on your data table a little blank or solvent blank we have to measure to correct for the solvent in the cuvette itself. And each cuvette's unique, right? Well, once we get that, we got to measure the intensity after over the initial. That's the transmittance. Do the negative log, we get the absorbance. So we usually use a phototube or a photomultiplier tube. Kind of cool how they work. That just converts the photons into electrons, right? So we're going to convert the photons into an electric signal, measure that ratio, sends it to a computer readout. Back in the old day, just, give you a printout. Now we just have a computer display. You're good to go. All right, so it's actually really kind of cool when you go in there and look at that. Ideally, I'd like to find an old one that I could open up and show you all the guts and pieces in there. But this is a fun lab. It's the only one we're going to do with spectrophotometry and general chemistry. And again, in organic, I think you're going to do some infrared work, maybe some nuclear magnetic resonance. Fun, fun, fun. But if you transfer, become a chemistry major, you'll be doing lots and lots of this cool stuff. All right, you should be prepared and ready to go for lab. You guys are awesome.